we're dealing with the knowledge area mechanics. We're going to review the 1D coordinate line which we did in the previous lesson. Now, in order to describe motion of an object, we must specify the position at all times and use some convenient coordinate system and a specified origin. Now, frame of reference. What is a frame of reference? A frame of reference is a choice of a coordinate axis that defines the starting point for measuring any quantity. So we have dealt with position along a line. Let's just recap. Position can be plus or minus on a coordinate line, and it gives an indication of the orientation. What do we mean by orientation? It gives an indication on which side the particular object or particle is. So the plus sign means that it is on one side of the coordinate line, and minus means that is on the opposite side of the coordinate line. And a coordinate line in 1D, which we deal with, has only two directions. So here we have a coordinate line, and that is our origin. So we have this side, we have this side, and we have this side. So this side is the positive side, and that side is a negative side. In a plane, however, we know if we had a plane, you can have many directions. So let's say that's y and that's x. Your vector or your particle can be moving in any directions. We are not going to be dealing with 2D or two-dimensional space. We're only going to look at motion along a straight line. Now, on a coordinate line, position of a particle is easily specified. For instance, if I say the particle has a position of +4, you will know where that particle is. That particle will be there. If we say the particle is at -8, we know if we're dealing with a coordinate line, that particle will be there, and we'll also know on which side of the coordinate line the particle would be. Now let's look at a position time graph. So in a position time graph, the motion is along a straight line in 1D. Yet the position time graph is not a straight line. Why is that so? Basically because now position is going to be described as a function of time. So if we look at our coordinate axis, I have our coordinate axis here, and we have the coordinate axis there. It's indicated on the vertical axis. And on the horizontal axis, we have time. Now let's assume that the position change after every 2-second intervals on the x-coordinate line. And we need to indicate the motion. So here we have x1, as you can see, that is x1, that's x2, and that's x3. So from the origin to here, it takes 2 seconds. From there to there, it takes 2 seconds. And from there to there, it's 2 seconds, right? So that is the elapsed time for that particle to when it changes its position. Now let's represent that. If we have x1, here we have x1, and it is at the plus 4. x2 is at plus 6. And then x3 is at minus 5. Right? So after 2 seconds, we got x1 here. The next 2 seconds, we have x2 there. And then the next 2 seconds, we have x3 here. And you can see these are, it doesn't seem, it's not a straight line, yet we know that the particle is moving along a coordinate axis. So if we join that like that, and there, we find that we get the motion of the particle on a position time graph. And if we look at this, we'll see that here, there, the particle or the object reverses direction. Here, it then passes the origin, and here it's on the other side, on the other side of the line. As you can see, it's there, right? And that gives you an indication that, okay, here, as you can see, it's on that side, and here we have it on the other side. The particle is on the other side. So it's very important to be able to translate a position time graph into a coordinate line, and a coordinate line into a position time graph. You should be able to do that quite easily. Now let's look at this position time graph. Here we have an object moving along an x-coordinate line. But here we've got the position time graph for this. So if we look at this, we see that particle moves from A to B to C, and there we say that from A to C it moves away from the origin and it goes towards the right, since we are on that side of the coordinate line. So A to C moves away from origin, right? And it goes towards, and it's on the positive side. If we look at CD there, it is at rest, because as time elapses, its position is still +3. From D to G, it reverses direction. As you can see, it's coming towards the origin. Once it's at G, and from HI, it's on the other side of the origin. That means from G going on to I, it's on the other side of origin. Right, now having this position time graph, can you then locate its position on a coordinate axis? So let's try that. Here, translating from a position time to a coordinate line. So if we have that, let's look at it. Here I have the coordinate line, and I've got a 0, +1, +2, +3, +4, since we had the coordinate here, there, right? I've shown that on a horizontal axis. Right, so if we have now A at 0 time, we find that we have A there, and if we represent that, we have A there, then we have B after that, and B has a position +1, so we have B. So here we have B, and then we want to show C, and we show C, and C is at +3, and then we see D is at the same position. So let's say if we take D, we have D there, and then we have E. As you can see, we have E, and E would be there. So we have E, and then we have F, and then we have G. But when we at G, I am now at the origin back to where we started off, and then from G, H, and I, it goes on the other side of the coordinate line. Right. So we have then H there, H, and we have I. So if you look at this, you'll see going from A to B, from B to C, C, D, it's on the same coordinate, E and F, here it's at the origin, and then it goes on the other side. Remember, all these, it's on the line. I've just displaced these alphabets, but it's the position of the particles is along the line. Now, let's look at displacement along a line. So, what is displacement? Displacement is a change in position, and it's given a special name. A change in position is actually referred to as displacement. If an object moves from position x1 to position x2, the displacement is given by x2 minus x1. From where it was to where it eventually finds itself. So the displacement would be the final minus the initial position. And here we're saying, let's assume that the displacement is happening during a constant time interval, and let's say it's happening during an interval of 0.4 seconds. Now, if we look at change in x, here we've got the coordinate line again. Right, we have the coordinate line again. And if we look at this now, here in this case, we see that change in x, which is the displacement, is equal to x2 minus x1, or I could have just said it's equal to xf minus xi, final minus initial. Now, if we look at this here, that would be our change in x. It has started off there. It starts off there and it ends off there. So if it starts off here and it ends off there, what would our change in x be? Our change in x would be minus 5, and this is in centimeters, so minus 5 centimeters minus the initial one is minus 3 centimeters, which then gives us minus 5 centimeters plus 3 centimeters, which is equal to minus 2 centimeters, as I have indicated it here, minus 2 centimeters. And the minus sign is telling you in which direction it is. So if we choose that as positive, then any direction that way is negative. So if we look at this, that is minus 2, minus 2. the same thing applies to this. Whilst this here, let's call this displacement A. Let's call that displacement A. That's displacement B. There's displacement C. And there's displacement D. So whilst if we look at A, it's in a negative direction, D is also in a negative direction, but A and D, they on different sides of the coordinate line. If we look at B and C, they also on different sides of the coordinate line, but they have the same direction. So the direction of displacement is independent of the side of the axis from the origin. Right, and that's important to note. Now let's look at velocity. Suppose you move steadily along a straight path. In order to predict where you will be at some future time, you need to know your present position, how fast you go, and your direction of motion. The quantity which tells you how fast and which direction something moves is called velocity. The average velocity v during some time interval, the average velocity v during some time interval is defined as the displacement divided by the time interval, during which the displacement takes place. So we can say that change in velocity, or the average velocity, normally we have a line on it, a bar, and the average velocity is equal to change in x upon change in t. Here your change in x is x2 minus x1 or xf minus xi. Now the sign of the velocity is determined by the sign of the displacement. Now suppose that each of the displacements on the coordinate line took place in 0,4 seconds. So we're saying assume that all these displacements that we have took place in 0,4 seconds. So then, if we look at the velocity here, let's say for V1, and we had determined that it is 2 centimeters, which means minus 5 centimeters minus 3 centimeters divided by 0,4 gives us minus 5 centimeters per second. The same thing would be for V2. Let's say we have V2 and see V2 is the initial is -2 and the final is 0, right? So in that case, it would be change in x would be x final minus x initial. So x final is 0 minus -2 divided by 0.4, so we find that the velocity is positive. It's moving in a positive direction. So that's your velocity. So what is important here is that you can see your velocity there and here is in the same direction, and there and there it's in the opposite direction. So the velocity does not tell you on which side of the coordinate line that particular particle is moving. So now let's look at a graphical representation. So if we have a velocity time graph representing a positive velocity, right? Here we have a velocity time graph. One has a negative velocity, other one has a positive velocity. If we look at that, can a displacement time during a time interval be determined from a velocity time graph? So can the displacement be determined from a velocity time graph? Well, during any interval, the position changes by an amount given by that equation. So we know what average velocity is. So here, change in x is equal to v change in t. And you can see v change in t is actually the height, times the base, or the area of the rectangle. If we look at this, so if we want the displacement from a velocity time graph, we get the area underneath that line. So we need to determine the area. Right. If we look at it here, normally when we have area, we would say that area is equal to height times base. But height is actually our speed or our velocity, and that is equal to 5 centimeters per second, and the time interval we're looking at is 0.4 seconds. So 0.4 seconds, which then gives us 2 centimeters, and that's plus, because we are taking the positive velocity, and that's plus 2 centimeters. And if we have that on a coordinate line, we know in which direction that particular arrow faces. Now, if we look at the negative velocity. Here I'm starting with that, and we have negative velocity. Negative velocity, so again we want to know what the displacement is. The displacement would be area is equal to height times the base, or like we say, length times breadth, but we want to know for 4 seconds, so that is the area under the curve. So we want to know that there, which means the velocity is minus 5 centimeters per second times 0.4 seconds, and that gives us minus 2 centimeters. Right, and the minus sign indicates the direction of your velocity, which in this case it would be v change in x is equal to v times change in t, which I have here indicated the v and the change in t. Right, so you have your change in x. So what we're saying is that from a velocity time graph, the displacement can be obtained from the area under the curve or line. Let's look at now the average speed. The average speed of an object, firstly, it's a scalar quantity. It is defined as the total distance traveled divided by the total time it takes for the travel. So the average speed of a particle along an x-coordinate line is equal to average speed, the total distance upon the total time. So if we look at our particle that was moving, and it was moving in that direction or in that direction, it's minus 2 centimeters or plus 2 centimeters. When we deal with average speed, we are not concerned which direction it moves. We're not concerned. All we're concerned about is the distance that it covers. So if we have to look at the average speed of these particles that we have, of these particles, and if it happens at the same during the same time interval, then the average speed is equal to then 2 centimeters. We're not worried about the sign here, and that happening in 0.4 seconds, and that will give us essentially the same thing that we have for velocity but without the sign, which would mean 5 centimeters per second. That's your average speed. Okay. Now let's look at this example. A cross-country runner runs from A to B via route X. So he runs via route X to B along the curved route and covers a distance of 14 kilometers. He returns to A via route Y, and there's the straight line route. His displacement from point A to B is 9 kilometers due east, represented by line Y. The total time for the run from A to B is 2 hours, and from B to A is also 2 hours. So what we need to do is calculate for route X the average velocity and the average speed. So here we have this. The runner goes from A to B and then on a curved path and then goes back to A using the straight path. We need to know what is the average velocity. So A, where V, average velocity, is equal to change in x upon change in time. The displacement is 9 kilometers, which is 9,000 meters, and the time is 2 hours. So we need to convert hours to seconds. So it's 2 hours times 60 to bring it to minutes times 60 to bring it to seconds, and we find that the average velocity is 1.25 meters per second. Let's assume we're taking that direction as positive. So that, or we could just say it's moving towards P or moving towards the east. Let's look at the next one, where we have, so that's 1. 2 says we need to determine the average speed of the runner. So average speed of the runner speed is equal to total distance divided by total time. Total distance we see is 14 kilometers, which means 14,000 meters, all upon 2 hours again, and that's divided by 60, which then gives us 1.94 meters per second. Okay, now what happens? We want to calculate for the round trip. That means going from A to B and B back to A. So what is the average velocity? So let's say B1 average velocity is V is equal to change in x upon change in time, which would mean change in x because the runner gets back to the original position here and he started off there, so that means that's 0 kilometers, or say 0 kilometers, and the time it takes is 2 hours. I could leave it in hours or have converted it to meters, doesn't matter. So this gives us 0 kilometers an hour. Right, so it's 0. There's no, the average velocity is 0 or 0 meters per second. Then we see if we need to have if we looking at the average speed, so average speed is equal to total distance divided by total time. And what is the total distance? The total distance would be 14 kilometers plus 9 kilometers back, which gives us 23 kilometers upon 2. The total time to go and come back is then 4 hours. Right? Remember, it takes 2 hours to go and 2 hours to return. Which means that this is equal to 23,000 meters all upon 4, and we convert it to seconds, and that gives us 1.60 meters per second. Right, that is the average speed, and we don't need to worry about direction. Let's look at this exercise. It says, what physical quantity can be measured from the area of a velocity time graph? We've dealt with that, and what can we get from the area? We get the displacement. Let's look at the next one. We have here Zara. Zara walks 70 meters east and then 30 meters west. The total distance traveled is 100 meters. So she goes 70 meters east and then 30 meters west. So the total distance is 100 meters. And that's shown by the dashed green line. But the displacement is shown as a red arrow. So there's the displacement. That gives you an indication of the displacement here. And it is 40 meters to the east. Suppose the walk takes 70 seconds to complete. What do you want? We want to know what is the average velocity. So the average velocity is equal to change in first we need to know the change in speed. Okay, so the average speed. So the average speed is equal to total distance over total time. Total distance is equal to 100 meters, and the time taken is 70 seconds, which then means that is equal to 1.4 meters per second. That's the average speed. What is the average velocity? Average velocity V is equal to change in x upon change in time, which is then equal to 40 meters. That's where how far it is from the original point, divided by 70 seconds, and that gives us 0.557 meters per second. Right? And that's its velocity, and that is equal to positive, as you can see in which direction your arrow is facing. Right, now let's look at this question here. How far can a cyclist travel in 2.5 hours along a straight line if her average velocity is 18 kilometers an hour? Okay, we have average velocity is equal to change in x, which is displacement, upon change in time. This implies that change in x is equal to the average velocity times change in time. Velocity we know is 18 kilometers an hour times time that it travels is 2.5 hours. That cancels out, and that gives us 45 kilometers. Right, so let's say for instance we chose that as the positive direction, then that would be plus 45 kilometers or 45 kilometers towards the right from its starting point. Now, does the car speedometer measure speed or velocity or both? So if we look at this, traditionally the traditional cars that we have measure speed. They measure speed. Now we're having more sophisticated cars with a lot of electronics. We find that it's possible for them to measure speed and indicate the direction of travel. So you can have them measuring speed as well as velocity. If we now look at the next question here, the position time graph for the motion of a particle, whose position changes from A to B to C to D to E. So on this position or this coordinate line, we see the different positions of the particle on this coordinate line. And assume that the position of the particle changes at 2-second intervals. So here we have the particle moving from A to B. That's the sequence. B to C, from C to D, and from D to E. And let's assume in terms of the time interval between each sequence there is 2 seconds. That's 2 seconds. From B to C it's 2 seconds, and that takes 2 seconds. 2 seconds, and that takes 2 seconds. So if we now have to draw a position time graph, let's look at that. So we have a position time graph, and we have time on this axis and x in centimeters on this axis. So if we now on this vertical axis plot the location, so we have say +2, +4, and +6, and +8. And we know this is our coordinate line, so it's -2, -4, -6, -8. But we don't have anything on the opposite side or towards where our coordinates are negative. So let's say we have A, so okay, and since we were talking about 2 second intervals, so that's 2, that's 4, that's 6, that's 8, and let's say that's 10 seconds. So here A is at +2, so we have A there. B is then at +4, we got B here. Then C is at +8, so we got C there. And D is then at +6, so we've got D here. And then E is back at +4, so we got E here. And if we now look at this, we find that that curve indicates the motion of this particle as a function of time. So this is essentially a position versus time graph. So what's important? If you have a position time graph, you need to be able to translate that and indicate the location of this particle that's moving along that coordinate line in terms of this 1D coordinate line. And alternatively, if you are given a particle moving in a one-dimensional coordinate line, you should be able to draw a position time graph for it. That's important. Now let's look at the next one. Given the position time graph, here you're given the position time graph, you asked to draw the position of a particle at A, B, C, D, and E on the coordinate line. So here you're given a position time graph which gives you an indication of the position of the particle with respect to time. So we need to translate this onto a coordinate line, and a coordinate line, remember, doesn't take time into account. It just locates its position and the movement of that particular particle or object. So if we have this here should be centimeter, and now here you're given the position time graph. We need to translate this into a coordinate line. So there we have that, which means we have 0, plus 2, plus 4, plus 6, and plus 8. And it's minus 2, minus 4, minus 6, minus 8 on the other side of the coordinate line. Alright, that's your origin. And if we look at this here now, A, and we look at A, and where's A? On that coordinate line is at plus 2, right? So remember, these are all plus, plus, like that, and I haven't shown the bottom, okay? Which means now here we have A, and that is here on the line, but I'm displacing it from the line. It's there, A, and then we've got B, which is at 4, so B, and then we have C, and C is at 8, so C is there, and then D is at 6, so D, we could just maybe take a different color just to show. So now D from C, the next is D, and D is at 6, and then from D the next one would be E, and E is at B. E is 4, so we have E there. And as you can see, that means we go like that, and like that, and like that, and there we go. This is essentially what we had here. So from this, you should be able to go to that, and from that, here, you should be able to draw this coordinate line. And that's important because, once you can translate or represent it graphically in terms of the particle movement as a function of time and on a coordinate axis, you will see that your understanding of equations of motion is going to become easier. So if you have, for instance, particle or the curve of a position time graph and you can translate that to a coordinate line, you will see that when you're dealing with equations of motion, you will have a much better sense of the direction of particles, the velocity of particles, and also on which side of the coordinate line you will be able to find a particular particle. But more of that when we deal with graphs of motion. So that's all for now, and see you the next time.